Hey, what's up YouTube? Today I want to talk about distance fields. It's a popular and well-documented topic, but I feel like most Unreal Engine tutorials only cover the basics. Today I want to dive a little deeper. Now, at first I didn't think I had much to say on the subject, but it turns out there's actually quite a lot. In this video, I'll first explain the theory behind distance fields, what they are and their key mathematical properties. Then I'll move on to the Unreal Engine side of things, discussing limitations, typical use cases, and how to use distance fields in shaders and Niagara. After that, we'll briefly go into some more advanced use cases of signed distance fields, like sphere tracing, cone tracing, approximating ambient occlusion, the jump flood algorithm, and basically why distance fields have become so popular in game engines in recent years. Finally, I'll cover techniques for baking and sampling static distance fields of your own, whether that's through my Game Tools add-on in Blender or directly in the engine using Scriptable tools, geometry scripting, and Niagara. Sounds good? Alright, let's dive in. What's a distance field? Simply put, it's a field that stores a distance to the nearest surface at every point within a given domain. In real-time applications, this domain is typically discretized. If you're working in 2D, that means using a texture where each pixel represents a point in space. And each pixel stores a distance to the closest surface. That's all there is to it. In 3D, it's the same idea, but with voxels instead of pixels. Each voxel holds the distance to the nearest surface. Now, this is often the actual real-world distance, so the values stored in the texture usually depend on your application's default unit. In Unreal Engine, that unit is centimeters, so the distance is typically stored in centimeters. That said, as long as you're consistent, you're free to encode values however you want. For example, you could store the distance in meters, and then simply multiply the sampled value by 100 to convert it back to centimeters. As you can imagine, these values almost always exceed the 0 to 1 range, which means the texture format needs to support arbitrary floating points values. Compression is generally not recommended, so most distance field textures are stored as 16-bit or 32-bit floats. So that's a distance field, or DF for short, but you're probably more familiar with the term SDF. The S stands for signed, meaning the distances inside objects are negative. That's really all it means. It's an important distinction though, because the sign tells you whether a point is inside or outside a surface. And that's incredibly useful for things like collision detection, surface interactions, and more. Now, even though you're working with a discretized field using 2D or 3D textures where each texel or voxel stores a distance to the nearest surface at that specific world space location, you can still get a reasonably accurate approximation of the underlying distance field continuous function when sampling the texture. And that's thanks to linear interpolation between neighboring texels or voxels. Of course, the accuracy depends on several factors, such as the resolution of the texture, the size of the domain, and the scale and complexity of the objects represented in the distance field. More on that in a second. A signed distance field is all in all a simple concept, but one with some very interesting properties. One of the first things you can do with distance field is compute its gradient to find the direction and rate of change, essentially its slope. Let's go back to the 2D example where each pixel stores a distance to the closest surface. And let's take it one step further back to 1D by looking at a single slice of this 2D texture. This black and white gradient can be interpreted as a height map representing the curve of the distance field function. It's discretized, so the curve appears stepped. But thanks to linear interpolation, we can approximate the underlying continuous function. If you sample this curve, this slice of a 2D distance field, at a given point, you get the distance to the nearest surface. Now, if you sample this curve again, but slightly to the left or right, you can compare the distances. And by using the known step size between the samples, you can compute the partial derivative, essentially the slope of the curve at that point. This tells you the direction of the greatest rate of change in the distance field. In other words, it tells you to get closer to the nearest surface, move in this direction, downhill. You can then follow that direction step by step, and eventually you'll arrive at a local minimum. Local because this method doesn't guarantee you'll reach the global minimum, which makes sense if you look at this next example. This method, called gradient descent, can sometimes quote-unquote trap you in local pockets known as local minima. This is an issue if you're trying to find the global minimum of a function using an iterative approach like this. But I'm getting ahead of myself. I'll give an example later in the video where gradient descent plays a small role. There's a lot to cover about gradient descent, and I've already made a video on the topic, so I'll skip the details for now. It's not even something we need to focus on at the moment. Reaching the local minimum is exactly what we're after here. It means you've arrived at the closest surface to your starting point. Now back to 2D. Just like we computed the derivative along one axis, we can do the same along the other by sampling the distance field slightly above or below, then comparing the two samples to derive the slope along that axis. Each partial derivative can be packed into a 2D vector, giving us the gradient of the distance field function, the direction of steepest descent. Since each pixel stores the distance to the closest surface, we can normalize this gradient vector and multiply it by the distance value to project directly onto that surface. And the same principle applies in 3D. By sampling slightly above and below along the z-axis, we can compute the slope in that direction too. The resulting gradient vector, once normalized, can also be multiplied by the distance at that point to land exactly on the nearest surface. So with just a texture that stores a single scalar value per pixel or voxel, we can not only sample the distance to the closest surface, but also the direction toward it, allowing us to project any point onto the nearest surface. Keep in mind that this technique has its limitations. Here's an example I'll explain in more detail in a moment, but essentially, I'm projecting a position, the position of this blueprint, onto the nearest surface, which is visualized by this sphere. And it works fine. Until it doesn't. But that actually makes perfect sense. Like I explained, the direction to the nearest surface is calculated using partial derivatives. The distance field is sampled at this position and also slightly offset along the x, y and z axes individually. The differences in the sampled distances along each axis give you the gradient of the distance field. By normalizing this gradient, you get a direction. However, there are cases where slightly offsetting the position, say along the x-axis, returns almost the same distance. And this may happen when the point you're sampling is equally distant from two surfaces. Like here, this point is nearly the same distance from both of these surfaces along the x-axis. So the derivative along that axis ends up being 0. There's no clear numerical indication of which direction brings you closer to the nearest surface. Mathematically, it's like you're at a local maximum, and computing the partial derivatives from nearby samples gives you a flat or zero slope. But the y and z derivatives might still return values, which can lead to an incorrect xyz direction being calculated. And that's why the sphere ends up projecting to the wrong place. There are workarounds though. You could take more samples, spaced more broadly, to take a more informed guess about the slope of the distance field at that location, and better figure out which direction leads to the closest surface. It's also commonly suggested to repeat the projection step multiple times to escape pitfalls like this. Even if your first projection is off because of a derivative issue, redoing the projection at the new location is, statistically speaking, unlikely to land you in another spot that's equally distant from two surfaces, if that makes sense. So even if you don't project to the closest surface, you do eventually reach a closest surface. Anyway, derivatives are pretty much an entire topic of their own in mathematics, and there are a lot more to say here. Moreover, using similar techniques, we can also derive the normal of the closest surface. Once the projection is done, we sample the distance field at that new location, slightly to the left, slightly to the right, to compute the gradient along that axis. The same approach applies to the other axis, whether you're working in 2D or 3D. The result is the gradient of the distance field function at that point. By normalizing this gradient vector, you get a unit vector that is the surface normal. Alright, the simplest way to experiment with distance fields in Unreal Engine is through shaders, using these two nodes. The first one samples the distance field at a given world location and outputs the distance to the nearest surface. The second one computes the gradient of the distance field function, using multisampling, just like we discussed earlier, which can be normalized to get the direction towards the closest surface. Understanding the underlying principles helps you immediately grasp the cost difference between the two. And if you dig into Unreal's source code, you'll find the HLSL code behind these nodes. It may read like voodoo magic because of the paging system and all that, but if you keep digging, you'll eventually find the information you need. Sure enough, the gradient node performs multiple samples, confirming that it's more quote-unquote expensive. Now, creating a signed distance field is a costly operation. For every texel or voxel, you have to find the closest surface. That essentially amounts to a collision detection problem and is usually optimized using spatial acceleration structures rather than brute forcing against every single triangle. Still, even with acceleration, this process is computationally expensive, so it's usually performed offline. Unreal Engine can generate a signed distance field for each static mesh asset. You can fine-tune the voxel resolution. The higher the resolution, the more accurate the distance field is, but also the more expensive the bake becomes. Since it's done offline, that's not a huge issue, but higher voxel density also drastically increases memory usage. If you're relying heavily on distance field, it's highly recommended to carefully consider how you design your static meshes. Take this asset for example. It's a worst case scenario for generating a signed distance field. The reason is simple. The top part makes the bounds large in X and Y, while the bottom part stretches the bounds in Z. And since this lower section is quite thin, you'll probably need to increase the voxel resolution to accurately capture its shape, which means a lot of memory is wasted on empty space. By splitting this static mesh into two separate assets, you'll end up with a distance field that's much more accurate and far more memory efficient. Now, unfortunately, as far as I know, this per asset distance field isn't really exposed. You can't do much with it. There's no built-in way to sample it directly, export it, or otherwise use it freely, which is a shame if you ask me. Instead, these per mesh distance fields are primarily used to be quote-unquote injected into the global mesh distance field. Comparing it to cascaded shadow maps is a helpful way to understand it. It's camera-based, it moves with you, and uses multiple resolution levels for near and far objects. It combines the individual distance fields from all static meshes into one unified field. Note that skeletal meshes are not included, and more generally, anything animated is excluded. That said, the transforms of static meshes can still be updated to move objects around, and their distance fields will be correctly updated in the global mesh distance field. And that global mesh distance field is what gets sampled when you use those two nodes. The first thing to keep in mind when sampling the distance field in a material is whether the mesh the material is applied to is itself participating in the global distance field. If it is, you'll likely encounter strange results, because the surface closest to itself is, well, the surface itself. However, the distance won't be zero, as the material is applied to the actual mesh on the quote-unquote surface at the pixel level, while the distance field is only an approximation of the surface. And this discrepancy can lead to odd artifacts. The solution is to prevent the mesh from participating in the global mesh distance field. So either set the distance field resolution to 0 in the static mesh asset and apply the changes, or turn off this setting in the static mesh asset properties. Note that this is not an absolute truth. Meshes can still very well participate in the global mesh distance field while having a material that samples it. It all depends on what you're trying to achieve. For example, if you're creating a distance gradient around objects, like to generate stylized ripples on a water plane, this could indeed become problematic. The water plane should not be allowed to sample its own distance field. The second thing to keep in mind when sampling the distance field in a material is whether the mesh is animated in any way, usually using world position offsets. As we've seen, the mesh distance field is generated through a costly offline process, done once in the editor. So any deformation applied afterward, like vertex offsets, won't be reflected in the distance field. And this can lead to noticeable discrepancies, most commonly self-shadowing issues, since vertices may end up inside the original volume used to generate the distance field. And unfortunately, there's no easy fix for this. The one lever you can tweak is the self-shadowing bias, but that only goes so far. So yeah, just a couple of important things to keep in mind when working with distance fields. Oh, and keep in mind, just like with shadows, you can use hacks, like having an invisible mesh participate in the global mesh distance field, while the visible mesh doesn't. This lets you create a kind of shadow proxy system, which can sometimes help you work around these limitations. Speaking of proxy system, there's actually a built-in feature that allows you to specify a custom mesh, so the distance field of one asset is generated based on the distance field of another asset, if that makes sense. Now, since UE5, something has changed, and the global mesh distance field seems to be partially broken. You may, for instance, get the distance to the nearest surface and remap it to the range 0 to 1 based on a given distance, and it seems to work. Until it doesn't anymore, or partially at least. And this can also be easily debugged using a simple sphere with one of its points centered at 0, 0, 0. Next, use a blueprint containing a plane to display the distance sampled from the global mesh distance field at the actor's position, while also printing the actual ground truth distance from 0, 0, 0 to the log. Keep in mind that the mesh itself should not participate in the global mesh distance field. Now, everything seems to work fine along the main axis, at least. The small difference we observe from the ground truth value is likely due to 16-bit floating point precision issues or something similar. However, this brings me to another limitation of the global mesh distance field. You can't sample it from anywhere in the world and expect it to return the distance to the closest surface. The global mesh distance field is updated using clip maps up to a certain distance around the surfaces. Beyond the highest clip map, the distance is clamped to the maximum value. This means that using the derivative trick to compute the gradient also won't work. Anyway, this ties back to the num clip maps CVAR. However, this doesn't seem to affect the actual meaningful maximum distance you can sample from the distance field, at least not that I can tell. It appears to be capped at around 500 centimeters, though the reason for this limit isn't entirely clear, to me at least. Things further go wrong when you veer off axis. The difference from the ground truth value skyrockets, and you can actually see a sudden jump in the value due to the clip maps. This seems to be tied to the clip map distance exponent CVAR. Changing it to 1.0 seems to completely break the distance field, and so does 1.1. But 1.2 seems to do something. Maybe even a little bit more? Yeah, it's somewhat smooth and round, so I'm not entirely sure. The default value is 2.0, so I'd expect it to be the right default value, so yeah, you'd need to see if changing this breaks anything. Anyway, I'm pretty sure it used to have much fewer issues before 5.0. We don't have much information on how or why, but word on the street is that it was reworked to be cheaper for sampling when using Lumen. And this raises two questions. What does Lumen do with distance fields, and is there a fix? For now, I'll focus on the latter. As far as I know, there's no easy fix. If you Google enough, you might come across a couple of CVARs that could make you think there's a solution, but the downsides are too significant to ignore. Essentially, they suggest turning off all cascades, which, in my opinion, is not a real solution. In my case, I couldn't get it to work at all. Setting the exponent to 1.0 seems to completely break the global mesh distance field, as I showed just a minute ago. Another potential fix is to use multi-sampling, as suggested by Matt. But again, to me, this feels more like a costly workaround than a true solution. It really depends on what you're trying to achieve. This essentially approximates cone tracing anyway and isn't technically a fix, but more on cone tracing in a minute. So if your goal is to get a smooth value from that single node, it's possible but only for short distances. Beyond that, it becomes problematic. It's a shame though, because it was really useful for things like stylized waterlines and similar effects. Since I'll be showing how to bypass Unreal Engine's built-in distance field system and use your own instead, I think this is still relevant. So let me walk you through a couple of examples. First, let's create a simple gradient based on the distance to the nearest surface. This outputs values in centimeters, so we'll create a gradient for, say, 100 centimeters. Clamp it to a 0 to 1 range, and then invert it to get a gradient that goes from 1 to 0. So far, nothing new. Now let's introduce time. I'm going to offset this gradient with it. As expected, this causes the effect to break. The time variable here is likely the time since you last launched the editor, so you're essentially offsetting the gradient by a huge value. Let's make the gradient loop between 0 and 1 using the frac node. Better. Now, this linear gradient can be converted into any other type of curve. The simplest way is by using a sine or cosine node. And let's go with the sine node, whatever. Save, compile. Good. However, as the distance increases towards the maximum, any pixel reading a value greater than this will share the same value due to the saturate node that clamps the value, right? Creating a blinking effect, if that makes sense. A simple fix is to modulate the signal with the original gradient. Let's keep the graph tidy. Save and compile. Cool, so the simple distance gradient now acts as a mask of sorts for the sine wave offset with time along the distance. And you can even add a power node to further control the fall-off. Let's use an exponent of, say, 4. Cool. And that's the basic idea behind stylized waterline effects. Once you understand how to convert any linear curve in the 0 to 1 range to any other type of curve, you can create the effect you're aiming for. For example, you can further offset the gradient using a 3D noise texture mapped to world position and even scroll it in the z-axis with time. Let's prototype this real quick. I'm looking for the, not vector noise, but the noise node. Let's construct an XYZ sampling position using the XY world position and the Z world position offset with time just to vary the noise over time. Okay, let's tidy up the graph real quick. And let's tweak the noise node settings. No turbulence, cheap 3D texture, single sample, and range from 0 to 1. Now we just have to scale the position to scale the noise. See, it works. We might want to fine-tune the strength of the noise added, so multiply, scalar parameter. Let's wear things up. And tweak the strength. Let's see what works best. Okay, that will do. Let's clean up the graph. So all we are really doing is offsetting the distance gradient before it's made to loop in the 0 to 1 range, right? And so you can also tighten the gradient around the middle value like this. Or you could scale the time. And adjust the gradient's initial falloff to create a different animation, meaning tweak the distance gradient so it's no longer linear before feeding it into the sine node. That looks a bit strange though. The speed is probably too low, and too much noise also. Anyway, you can see the effect the power node has. The higher the power, the quicker the effect expands at first and then it slows down. With an exponent smaller than 1, it starts slow and expands rapidly, which doesn't look natural here. Anyway, you get the idea. Let's clean up the graph. Next, let's incorporate the distance field gradient. We can normalize it to get the direction away from the nearest surface and compare it to a world direction. Let's use 1, 0, 0 for now. Using a dot product will create a value within the -1 to 1 range. -1 when the directions are opposite, and 1 when they are similar. Again, it's all about remapping this gradient from its current range to any other range that suits your effect. Let's simply saturate the result to remove negative values, and then multiply our signal by this. This creates a cone effect in that world direction. You can further tighten this cone using a power node, for example. Save and compile. You get the idea. I'm sure I'm not teaching you anything new at this point. Alternatively, you could remap the dot product result from -1 to 1 to a 0 to 1 range, so the effect isn't entirely removed when the directions are opposite. And let's double check the node's settings are correct. Yeah. We could also introduce more ripples. For instance, we could multiply the initial gradient by 4. This could also be a good time to sample a curve atlas instead of using a sine node, allowing for more artist-controlled animations and so on. There's a lot that can be done with this. For instance, this direction could be derived from a tangent to the mesh, and this would be ideal for creating directional effects along a river mesh of some sort. Or similarly, using a blueprint to spawn spline mesh components along each segment of a spline, like this one. It's out of scope of the video though and isn't anything particularly complex, so I'll just let you pause the video to take a peek at the blueprint instead. Keep in mind that nanite might cause issues as usual. So either disable it or make sure tangents are working correctly first. They're computed based on the UVs, so it's something to keep in mind. Anyway, you could convert this forward vector along the mesh from tangent space to world space. This gives you a mask effect that follows the spline, if that makes sense. You could use this to push vertices up in front of obstacles and down behind them, following the principles I just explained. Or you could use distance fields for more random effects, like some sort of repulsion effect or something. Distance fields are awesome. Here's one last example. Instead of generating shorelines mathematically using sine waves based on distance and so on, you can simply map a texture. The concept is straightforward. Use the distance as the v-coordinate and the gradient or direction away from the surface, converted to a normalized angle, as the u-coordinate. It looks like this when using nodes. The v-axis is simple, but the u-axis is a bit more involved due to the trigonometry and converting an angle in radians into a normalized 0 to 1 value. These two values can then be combined to create UVs for mapping the texture. And you can manipulate these UVs just like any other. For example, you could shift the v-axis over time to scroll the texture, or scale it along that axis and so on. Keep in mind, you'll probably want to fade out the texture with distance, right? Now, there's one thing to keep in mind. See this harsh line? This is expected, and it comes from the GPU computing the UV gradient to decide which mipmap level to sample from the texture. Basically, when the u-coordinate goes from 0 here to 1 all the way around, and then back to 0, there's a sudden jump from 1 to 0 in essentially a single pixel. The GPU interprets this as seeing this pixel, that fragment, from very far away, since that's probably the only reason it would read such a large jump in UVs. As a result, at pixels where there's a significant jump in UVs, the texture is sampled at its highest MIP level, which is essentially an averaged color of the original texture, and this causes the visible line. To avoid this, you'll need to provide your own derivatives. This can be as simple as supplying the derivatives in x and y of a gradient that doesn't have that sharp jump but still maintains a similar slope, like the world position scaled to some extent. You can eyeball it, it's unlikely to cause major issues aside from blurriness. See, I can cheat and force the texture to sample its highest MIP. Anyway, you get the idea. Using distance fields in shaders usually involves combining distance with a gradient to create various effects. Now, this is cool, but the potential of distance fields goes far beyond just creating stylized shorelines and these neat little VFX. It's actually amazing to see how such a simple concept, a field of sine distances, can have so many applications and play a role in so many algorithms. I already covered one such algorithm in a previous video, so I won't go into detail again here. But sphere tracing is a particularly interesting use case of distance fields used to efficiently sweep a sphere through world space along a given direction. In a nutshell, the naive approach would be ray marching. You take incremental steps along a ray, sampling the distance field at each point to check if the sphere fits at that location. In other words, you compare the distance to the nearest surface with the radius of the sphere. Sphere tracing improves on this by taking advantage of the fact that sampling the distance field gives you the exact distance to the nearest surface. So instead of stepping blindly, you can often take much larger, more informed steps. In the worst case scenario, the closest surface is directly ahead, and you land exactly on it in the next step, which is totally fine. So that's sphere tracing. Again, I'll refer you to one of my previous videos for more in-depth explanation. Still, to avoid leaving you hanging, here's a basic implementation of sphere tracing. It's an example I didn't have the chance to show in my previous video. So I'm using an instance static mesh component to spawn a few spheres. The goal is to visualize each step of the sphere trace with its corresponding sphere. To achieve this, I'm using a single custom per instance data to store the instance index, which lets me isolate each sphere in the shader. Speaking of the shader, I create a dynamic material instance to set the number of spheres, which corresponds to the number of steps I'll take along the sphere trace. In the shader, I can access the instance index stored in the custom data and divide it by the total number of steps to get a normalized index. This allows me to linearly interpolate two colors along the ray. Next, I get the actor's position and make it relative to the camera. This is mandatory for sampling the global mesh distance field in HLSL through a custom node. I also transform the actor's forward vector to world space. Then I provide the number of steps to take, which is capped at the instance index. For example, if the second instance is meant to visualize the second step along the ray, it should stop at that point, right? In the HLSL code, I initialize the first step's position. For each step, I sample the global mesh distance field to sample the distance to the nearest surface. If the distance is smaller than the sphere's radius, it means there's a hit along the ray at that step. In that case, I simply output a Boolean value for the hit variable along with the step index at which the hit occurred and the hit position. Now, if the sphere can fit at that location, I march forward along the ray in that direction by at least the distance to the nearest surface. If the loop reaches its end, it means the sphere trace has traveled as far as it could without hitting any surfaces. The hit position is then transformed back to absolute world space. Since we are building a vector that is meant to offset the current vertex position, well, I subtract that initial vertex position and offset the vertices along their normals based on the sphere's radius to reconstruct the sphere instance at the hit position. And voila, each instance is positioned at each step along the sphere trace, letting you visualize what's happening behind the scenes. Each step size matches the distance to the nearest surface, which can be an advantage, as the sphere trace can move quickly through open space with few steps. However, it can also be a limitation of some sort, because traces near obstacles may only move forward by the distance to the obstacle, which could be small. As a result, many steps are often wasted around shapes, and the trace may thus not even travel that far. Similar to sphere tracing, there's also cone tracing. This technique is widely used to approximate occlusion, and it's actually what the skylight uses to compute ambient occlusion when lumen is not enabled. That said, lumen also relies on distance fields using somewhat similar-ish algorithms to gather information about the scene. So the principle is similar to sphere tracing and can be loosely approximated using a simple setup, like this graph here. It's a cleaned up version of this. The key idea is that the distance field doesn't have to be sampled exactly at the current fragment's world position. It can be offset, for example, along the surface normal. Let's say you want to compute ambient occlusion at a specific position. You define a cone angle, then take steps along the cone's direction, which can be the surface normal, sampling the distance field at each step. Using the sampled distance, you can approximate whether the cone intersects geometry. If the distance is smaller than the cone's radius at that step, you increment an occlusion value, typically based on things like the distance delta, step size, cone falloff, and other weighting factors. The exact implementation may vary, but that's the general idea. You can also compute what's commonly referred to as a bent normal. Instead of accumulating a scalar occlusion value based on cone intersections, you use the distance field gradient to nudge the cone direction away from nearby occluders. This gives you a vector that points towards the direction of least occlusion. This approach is useful for sampling a cube map or light probes with a more informed direction, resulting in a more accurate representation of the light source. This is a simple and rough approximation though. Typically, the go-to implementation relies on multiple random sphere traces using a uniform distribution, often with a Fibonacci hemisphere or something similar. For each step along each trace, you increment a vector by that step. The result is a vector that sums all the successful steps from all traces. Once normalized, this gives you the bent normal. And this works because essentially a ray that travels a long distance will have a higher weight in the average, while a ray that hits a surface early won't contribute much. So once normalized, the resulting averaged vector provides a good approximation of the unoccluded direction, if that makes sense. The length of the bent normal before normalization can give you an idea of how much ambient occlusion is present. For example, if most rays are able to travel farther on average, it suggests that there's little occlusion at that point. And if I'm not mistaken, that's exactly how the skylight's distance field ambient occlusion feature works. Smart. Now, to be honest, I'm not an expert in cone tracing or approximating ambient occlusion with it. The concept is fairly simple in principle, I feel like, but as usual, the devil is in the details. There are many ways to implement such algorithms, each with its own small caveats. Unreal Engine has a built-in function to approximate AO using the global mesh distance field, so you can check the source code to get started on your own algorithm. Here's some code that handles the global mesh distance field clip map system. It's not specific to the ambient occlusion algorithm, so whatever. This is though, and as you can see, there's not much to it. Start with an occlusion value of 0 and an initial weight of 0.5. This is used to track the total weight for computing the weighted average. For each step, compute the step distance from two arbitrary values, depending on how far you want the trace to start and end. Sample the global mesh distance field at the world position, relative to the camera, and offset along the world normal multiplied by the step distance. Next, increment or decrement the occlusion value based on the weight of the sample at this step and the ratio between the step distance and the distance to the closest surface. Keep track of the total weight, reduce the weight of the next step by half so it contributes less and less to the total occlusion. Finally, increase the step size, in other words, step forward along the ray. Repeat this process and normalize the final occlusion by the sum of all weights. So it's not technically cone tracing. It simply samples the global mesh distance field at increasing distances from the surface. If there are no obstacles at all, the ratio between the step distance and the distance to the nearest surface is always 0, meaning no occlusion occurs. So it's very rudimentary, but it's a great starting point. I feel like the key takeaway here is to get comfortable with for loops and understanding the space you're working in. Does your distance field function expect a world position relative to the camera, or a UVW unit coordinate when sampling a volume texture? Depending on that, the stepping can be done in world space and then converted to UVW if necessary, or you can convert the position to UVW ahead of time and do the stepping in unit space. Same idea, but different approaches. And as you can see, with very basic HLSL, a single for loop, a single texture sample, and a bunch of additions and multiplications, you can start building cool algorithms like this. The global mesh distance field can be sampled just as easily in Niagara. There are plenty of modules that offer basic functionality, but I always encourage people to understand the underlying principles so they have the freedom to implement things their own way. So let's create a new Scratchpad module and start by adding a collision interface input. From that input, you can drag a pin and search for distance field related functions. You can then say, hey, let's sample the distance field at that particle's position. Using the distance to the nearest surface and the distance field gradient, we can offset the particle's position in the direction of the closest surface, multiplied by the distance itself. That effectively projects the particle onto the nearest surface, right? From there, you can do a bunch of interesting things, some of which I've already demonstrated in other videos. For example, you could offset the particle slightly downward each tick, and then reproject it onto the nearest surface every frame. This essentially performs a form of gradient descent along the vertical axis, causing the particle to eventually settle into a local minimum of the distance field. In Niagara, you can also implement things like sphere tracing, cone tracing, and a bunch of other cool tricks. Again, I'd recommend checking out my previous videos for examples, and I also encourage you to dive into the existing distance field related Niagara modules to see how they work under the hood. They are great learning resources. Also, remember when I mentioned that the distance field UE generates for each static mesh isn't really accessible? Well, I may have exaggerated a bit. Niagara actually allows you to sample the per asset distance field through the rigid mesh collision interface. I'll get into that interface a bit more in a moment, but in summary, I've found this particular technique to have some serious limitations. Maybe I'm doing things wrong though. For example, one function consistently returns a distance of 0 for some reason. Another one gives you a very rough distance field with visible boundary issues. It's also unsigned, so you can't tell whether you're inside or outside the mesh, which makes ray marching pretty tricky. On top of that, it seems to be narrow bounded, meaning the distance values are clamped to fairly low ranges, which ends up breaking the ray marching shader when you try to push the distance checks too far. There's a third option that behaves a bit better, but it's still unsigned and has the same limited range issue. So yeah, I don't know. Maybe still worth looking into for certain use cases. Alright, let's assume you don't want to enable distance fields in Unreal Engine for any reason. This means you can't use built-in distance field features, but that doesn't mean you can't use your own distance field, right? Let's go through an example. Here's a quick test scene from my board's example. This Niagara system uses the global mesh distance field to query nearby obstacles and such. Nothing too fancy. Now, let's assume this approach isn't an option. I'm going to export the scene as an FBX file. Next, I'll import it into Blender and remove anything unnecessary. Collisions, empties, lights, and so on. I only care about the meshes. And let's assume I'm not worried about the ground. Now, I'll use my free and open source Blender Game Tools extension, which is available as an official Blender extension, to bake a signed distance field. You just need to go to the preferences, search for the Game Tools extension and click install. First, I'll merge these rocks and voxelize them for the best result, since my SDF baker still doesn't handle self-intersecting meshes well at the moment. So this is a quick workaround. and the faceted look is bothering me, sorry. Set smooth? No? Oh, that, better. Next, I'll create a cube, scale it, and position it to define the domain where I want to sample the signed distance field. I'm being a bit finicky during this step, so I'll fast forward. In the SDF Baker panel, I'll select this cube as a custom bounds, save the Blender file, important, and set the resolution to 128/64. Then I'll select everything and click Bake. This may take a while depending on your scene. Upon completion, by default, an FBX and EXR file should have been created in the same location as a blend file, but this can be customized. Anyway, these files can be easily imported into UE like so. For the EXR file, let's configure it to be 16-bit floats. So not the format I'm highlighting here, it's a mistake. Right-click on the texture asset to convert it to a volume texture. Make sure its format is still 16-bit floats, and fine-tune the resolution as specified during the bake, so 128 in X and Y. Now let's import the FBX and drag the mesh into the scene at 0, 0, 0. This allows me to use the mesh bounding box as UVW coordinates to sample the volume texture, ensuring that the baked signed distance field accurately represents the scene. And the simplest way to double check this is to use a height fog with volumetric fog enabled and just a little bit of fog. Let's create a material, switch it to volume and set it to additive. Then we'll use a bounding box based UVW node, plug that into the UVs of a texture sample, select the volume texture, and remap the distance like so. For example, we can create a 0 to 1 gradient with distances ranging from 0 to 10 cm or whatever works, and plug that into the extension pin. Assign the material and you may also need to disable nanite on the static mesh for this particular case. And voila! Our distance field is indeed correct. Great! Now this quick hack only works because the mesh perfectly matches the distance field domain. But let's say we have the world position of a particle and we want to sample that distance field. We'll need a formula to convert that world position into UVW coordinates. Now, if the distance field is world aligned, and to keep things simple it usually should be, the formula is straightforward. You subtract the domain's center point from the world position, divide by the domain's extent, and add 0.5. However, since getting the center point of the domain can be a bit of a hassle in our case, because the mesh being offset and all, there's a simpler workaround. Instead, you can subtract the minimum bounds to the world position, then divide by the difference between the maximum and minimum bounds. And this converts a world position into a UVW coordinate in the 0 to 1 range within the domain. If the world position lies outside the domain, the resulting UVW coordinates will fall outside the 0 to 1 range. Sampling the volume texture at that point will cause it to tile, which is usually not what you want. To avoid this, it's best to use clamp addressing to ensure the UVWs stay within bounds. And with that, we have valid coordinates to sample the baked distance field. This lets us recreate this Niagara system using our own static distance field. Concretely, in my custom module, where I sample the distance field, instead of using the collision query interface to sample the global mesh distance field and project the position onto the nearest surface using the distance field gradient, as I explained earlier, I do the following. I first convert the particle's world position to UVW coordinates based on the domain bounds using the formula I just described with the min and max bounds. Next, I calculate the size of a single voxel in the texture in UVW space. Then, using the UVW coordinates, I sample the baked distance field to obtain the distance. I derive the distance field gradient by sampling nearby points along each axis. This gradient provides a direction which, together with the distance, allows me to project the world position onto the nearest surface. Or at least try to. Finally, I convert the projected world position back into UVW coordinates. At this point, I sample the distance field multiple times to compute its gradient at this position and obtain the surface normal. Thus, I'm able to recompute all the necessary information I initially obtained using the collision query interface to sample the global mesh distance field, but this time with a baked distance field instead. Of course, this method is more limited. UV's global mesh distance field is far more powerful, thanks to its camera-based clip map system that dynamically merges static mesh assets into a single unified distance field. But again, this is just a basic example to show that simple workarounds do exist. Oh, and also, working with non-axis aligned distance field domains is definitely possible, but at that point, simply using the min and max bounds to transform your world position into UVW coordinates won't be enough. You'll likely need to construct the domain's transform matrix and apply a proper matrix multiplication instead. And that's something I touched on in my neighbor grid 3D video. I'll also dive into this in more detail in an upcoming video dedicated to ray tracing and ray marching. On a similar note, signed distance fields can be baked directly in Unreal Engine using geometry scripting. And this process is fairly straightforward, although it does require a bit of hack to work around the limitation. First, enable geometry scripting. Then create a blueprint using the generated dynamic mesh actor class. And create an empty volume texture. In the blueprint, implement the onRebuild generated mesh event. Reset the mesh and copy the desired static mesh asset. Let's make this a public variable that you can tweak. And technically, all you need to do is call the bake signed distance to volume texture node. Wire in the dynamic mesh and specify the volume texture we just created. Feel free to explore the available options, such as the number of voxels, compute mode, and more. There's also a scale and offset setting for the distance to bake. Now, if you place this mesh in a level, the volume texture should update accordingly. But notice there's one catch. The signed distance field is strictly limited to the mesh's bounds, and you'll likely want to sample the distance field from a bit farther away from the surface. So ideally, there should be a bounds offset option, but unfortunately, there isn't one, unless I missed something obvious. That said, I found a workaround. I'm going to select all the vertices, and compute the mesh bounds. Using the min and max bounds, which I can offset as needed using two variables, I'm going to create a list of positions representing the 8 corners of my custom bounding box. And then I simply add a vertex to the mesh at each corner. And this trick is enough to make the node think the mesh is wider than it actually is, without apparently affecting the signed distance field generation. And this idea could be iterated on. You could, for instance, create a tool where you drive a box volume in the scene, and any geometry within that box gets cut out using a Boolean operation to generate signed distance fields at desired locations. Lots of potential there. And I couldn't resist giving that idea a try. I'll just quickly go over what I created to keep the video somewhat short. So the entire logic is contained within a generated dynamic mesh actor. Since it's computationally expensive, the first thing I did was enable the frozen option to prevent geometry scripting from rebuilding the mesh every time the blueprint is dragged in the viewport. Instead, mesh generation is triggered manually via a function that can be called in the editor. In that function, I first reset the mesh. Next, I sanitize the mesh, material and texture asset path, nothing too exciting, so I'll skip the boring details. Then, using a box component, I retrieve all actors overlapping it. This list of actors can be further filtered using tags. For each actor, and for each scene component within that actor, I request a mesh from the dynamic mesh pool. I then copy the mesh found in that scene component to this temporary mesh. This individual temporary dynamic mesh is then added to the persistent dynamic mesh at the actor's transform relative to the blueprint's own transform. Essentially, the idea is that the copy mesh function copies the mesh in local space, regardless of the component's transform. But we want the copy to match the component's world transform. However, since the dynamic mesh we are building is also attached to this blueprint tool, it inherits its transform. So we need to walk through a few steps to get everything in the correct position. Finally, I release the mesh. This effectively creates a single mesh containing every static mesh found within the box volume. The last step is to cut out any geometry outside the box. And to do this, I create 6 planes to perform 6 mesh plane cut operations. I then apply the custom bounds hack I mentioned earlier, adding a vertex to each corner of the bounding box. At this point, I could generate the signed distance field, but I wanted to try something different. I wanted to improve the user experience by creating a new static mesh asset, placing it in the world, and generating a new volume texture sampled in a new material assigned to the static mesh. In summary, I wanted to get an instant preview of the bake, and I accomplished this using a Python script. The steps are fairly straightforward. Call the execute Python script node, add the necessary inputs for the Python script, and that's specific to the Python script you're going to run, and define the outputs you want to receive. Next, in your project folder, within the content folder, create a Python folder and add your Python script there. I won't go into too many details, since this isn't a video on Python scripting, but essentially the script creates a material asset, a volume texture asset, configures the material, and within the material creates a few nodes, along with the necessary connections. Once the script is placed in the content/Python folder, just restart Unreal Engine, and this folder will automatically be added to UI's Python system path. That way you can import the Python file and call whatever method you need from the script, passing the required arguments to retrieve the created material and volume texture assets. Note that you can write any Python function directly within that node, but I think it's useful to know how to import a Python file as a module, so I wanted to demonstrate that. Additionally, many asset utility functions available in Python are also accessible in blueprints. You can easily create a new material asset and construct its graph, wiring nodes and all, directly in blueprints. However, it can be a bit cumbersome to do everything with nodes, and UE's Python API usually offers more flexibility than blueprints. Anyway, now that I have a reference to the volume texture, I can call the bake signed distance to volume texture function. Next, I reset the mesh and replace it with a box that matches the custom bounds. I also flip the normals. This is a well-known trick for ray tracing a box even when inside the box. Finally, I create a static mesh asset from this dynamic mesh. I store the axis-aligned bounding box minimum and maximum values as metadata, just for good measure. Then I spawn a static mesh actor, assign the static mesh, set the material, and reset the dynamic mesh. Voila, now this blueprint can be placed anywhere in the world. Just click the button to bake the signed distance field into a new volume texture, along with the domain bounds, which are baked as a static mesh that gets placed immediately in the correct position with a debug material applied. That material, by the way, is a translucent material with depth testing disabled. It contains a function that first performs a ray box intersection test to calculate how far the ray travels through the distance field domain based on its minimum and maximum bounds. This distance is then used in a simple ray marching algorithm. While it's a bit outside the scope of this video, the basic idea is that I divide the ray into a set number of steps, and at each step I sample the distance field to check if I'm close enough to a surface using an arbitrary distance threshold value. If I am, I refine the hit location within the signed distance field using binary search. At that location, I calculate the surface normal using the derivative technique I explained earlier in the video. If a ray hits a surface, the function returns 1 along with the normal, otherwise it returns 0. And those outputs are used to drive the emissive color and opacity. That's the general idea. Again, I'll probably make a dedicated video on ray marching, so I'm keeping it brief here. If you want to dive deeper into the topic, I recommend reading Ryan Bruck's blog post. Anyway, this process can be repeated indefinitely. Very cool. The possibilities are endless when it comes to building tools for baking distance fields. Here's another one I experimented with using Scriptable tools. I've already made a few videos explaining how to use Scriptable tools in detail, so I'll skip over the specifics this time. First, let's take a quick look at the tool in action. This Scriptable tool lets you specify a list of actors. For each actor, it tries to find any spline components and uses them to determine the 2D domain for baking the distance field. You can then fine-tune the domain bounds, set the texture resolution, and click Accept. And just like that, you get a distance field for all the splines. And this can be used for cool things like shoreline VFXs and more. It could even be done in 3D, perhaps using Niagara to bake into a volume texture, but I chose to keep it simple and work in 2D. Now, the Scriptable tool blueprint itself isn't too complicated. In the script setup, I add a property set to list the actors I want to include and customize the texture resolution, as I just demonstrated. The core functionality happens in one main function, which runs both on tick and when the accept button is clicked. The tick function doesn't draw into the texture though, it just gathers data. So for each actor listed, I retrieve all spline components, and for each spline, I get the number of spline points. I then extract the 4 control points for each spline segment. From this, I compute the spline's conservative bounds. Conservative because while the spline could technically fit into a smaller bounding box, we are playing it safe. Next, I create a list of all spline segments storing their control points. Each spline's bound is compared against the global bounds, which are initialized with very large values at first. The goal is to construct the overall bounds that fit all the curves. The global bounds are then tweaked based on user parameters. Next, if this function call is meant to draw into the render target, I initialize it by setting its size and filling it with a large initial distance. I create a dynamic material instance, sending both the texture parameter and the global bounds. Then for each spline segment, I essentially perform a draw call, sending the appropriate spline control points each time. These control points are used in the material to sample the curve in the render target. Now this is a brute force approach. For every pixel in the render target, I sample many points along the spline, compare the distance to the pixel, and output the smallest distance. It's then compared to the distance already stored in the render target using a min operation, layering each spline into the texture. And that's basically it. Oh, and on script render, I simply draw 4 debug lines based on the global bounds. That's it. So yeah, I'm not a huge fan of this brute force method, but it's a proof of concept. There are mathematical tools to find the exact point on the spline closest to any point, but they involve intricate route finding algorithms that probably aren't easy to implement in HLSL, so I didn't even bother. Gradient descent might be another approach worth exploring. However, since this is an offline tool and performance isn't a huge concern, you can just go crazy with the sample count and the brute force method should work just fine. Another common technique for generating signed distance fields is the jump float algorithm, which, once again, I've explained in detail in a previous video. I feel like I've said this a lot in this video, but hey, it's a fact. Anyway, the GFA algorithm allows for baking signed distance fields in real time with decent performance, making it quite interesting. In a nutshell, the idea is to generate the outline of a shape, either in 2D or 3D. This outline is called the GFA seed, and it's used to propagate the seed's coordinates to nearby pixels based on the closest distance. This process ultimately allows you to generate the distance field through a distance check, if that makes sense. Then, as a last step, you ideally check if the pixel or voxel is inside the shape to generate a signed distance field. Now, here's a quick experiment of mine. I'll keep it brief though, since this video isn't a tutorial on advanced use cases with Niagara. This is more of a very rough example with, let's be honest, very limited applications. It might give you ideas though. I first imported a skeletal mesh along with an animation. In a Niagara system, at the emitter level, I created a render target volume that points to, well, a render target volume asset. I also created a rasterization grid 3D, a grid 3D, and a skeletal mesh interface. Its skinning mode is set to preskin, and the mesh is retrieved by looking at the parent component. And sure enough, in a blueprint, I parented this Niagara system to a skeletal mesh component, which plays this animation by default. This skeletal mesh also has a region with uniform sampling enabled, which is specified in the skeletal mesh interface. I also have user-exposed vectors for controlling the bounds, min and max, which are visualized using a box component. And these are used to set the location and size of the cube representing the distance field domain. This cube, by the way, uses a material with the same material function I briefly mentioned a few minutes ago. It performs a simple ray marching algorithm and calculates the surface normal. In the Niagara emitter, here I initialize the grid and render target sizes, nothing fancy. Then I compute the number of GFA steps based on the volume render target resolution along each axis. This is one of the key properties of the GFA, right? It has n log n complexity. Next, I dispatch a compute shader an arbitrary number of times. The more times it's called, the more accurate the voxelization becomes. For each call, I randomly select a coordinate on the skeletal mesh surface, using a uniform distribution thanks to that node and this region's setting. This allows me to sample the world position on the skeletal mesh. I then convert the world position to a unit position based on the bounds, min and max, and further convert it to a cell index based on the number of cells in the rasterization grid. Finally, I ensure that any voxel containing a particle is assigned a value of 1, otherwise it gets a value of 0. Next, I read the rasterization grid value, and if it is 1, I write the voxel world position in the 3D grid, along with that 0 or 1 value in the alpha channel. And so if I simply output this to the render target volume, you might see that it somewhat voxelizes the skeletal mesh. However, this isn't entirely accurate, as we are voxelizing randomly scattered points on the surface of the skeletal mesh, so it's approximate at best and only provides surface data. I couldn't find a way to voxelize the entire skeletal mesh volume, but still, I thought this was interesting enough to share. After voxelizing the skeletal mesh surface and writing each voxel's coordinates where the mask isn't 0, essentially creating the GFA seed, I can perform the GFA algorithm. It's separated across each axis individually for better performance. Head over to my video on the GFA for more details. Essentially, this algorithm efficiently propagates data based on the smallest distance. And that data is the voxel world coordinate. In simple terms, it fills the remaining voxels with the coordinates of the closest voxel. Once the entire grid is filled with coordinates, I can compare those coordinates with the voxel positions to generate the distance field of the skeletal mesh surface. Keep in mind, though, this isn't a signed distance field. There's no knowledge of what's inside the skeletal mesh, and I couldn't find a solution to that. I had a few ideas, but they either worked only for convex shapes or were way too complex for my skills. So yeah, it's a non-signed distance field, which admittedly makes ray marching trickier since you can't detect a boundary change. In other words, you have no knowledge of when a ray goes through the surface. But still, it allows you to generate a distance field at a reasonable cost, and you could use it to create some cool effects. A simpler and probably better alternative, considering the few use cases I have in mind for generating a 3D SDF of an animated skeletal mesh, would be to approximate the skeletal mesh with primitives attached to bones and analytically compute the signed distance field of each shape for every voxel. It'd be a coarse representation of the skeletal mesh, but it could be precise enough for many use cases. and turns out the rigid mesh collision interface allows you to do just that. And guess what? I've also made a video dedicated to that interface. Links will be in the video description below. It comes down to creating a rigid mesh collision interface to search for actors with a specific tag. During the emitter update stage, call the find actor function from this interface to perform a box overlap check to locate actors with the designated tags. Next, iterate a 3D grid interface and convert each voxel's unit coordinate to world position using the domain's min and max bounds to calculate the closest distance to any primitive found in the actors. Finally, output that distance to a volume render target with a size matching the 3D grid. And that's basically it. The resulting signed distance field can be ray-marched and used as needed. Cool. Many might initially think there's not much to say about distance fields, myself included. But while working on this video, the more I delved into the details, the more I realized I could go on for hours. There's so much to explore. For example, capsule shadows use the distance field of capsules to calculate soft shadows. Yes, you can ray trace shadows from a signed distance field and generate great looking soft shadows almost for free. Combining signed distance fields is another complex topic. Many people assume you just take the minimum distance between the two, but it's actually way more complicated than that. This website is the gold standard for distance fields, and many other topics actually. So if you want to dive deeper, I highly recommend giving it a read. That's it. I hope you enjoyed this video and learned something new. If you did, consider leaving a like and subscribing to the channel. I've also built a project with a bunch of cool examples, some of which were featured in this video. It's available as a tier 2 reward on my Patreon, so if you want to get your hands on the project or just support me, consider joining. Any support is much appreciated. Thanks for watching, and thanks to all my patrons for the incredible support. I'll see you in the next video. In the meantime, take care of yourself. Bye bye!